So up till now we have used the flexure formula for various cross section like circular section, rectangular section, square section, T section, I section, symmetrical I section, unsymmetrical I section. Even in the case of rhombus also we have find out the bending stress. And for finding the value of the bending stress, that is the maximum value of bending stress, we are using the flexure formula, which one is sigma b maximum divided by c is equal to m by the moment of inertia I. And normally we take the value of c is the maximum distance between the neutral axis and either the top fiber or bottom fiber. And we have introduced one more term, that is a section modulus, which is represented by z, is same as equal to the moment of inertia I divided by c, which is the maximum distance between the neutral fiber and the top and bottom fiber. Section modulus is also called as the elastic section modulus, and it depends upon the geometry of the cross section, that is depend upon the value of I, and moment of inertia is a strong function of the cross section. So if we rearrange this term, in that case we get the maximum bending stress is same as equal to m, and this c will shift in the denominator of I, that is we have m divided by I by c, which is same as equal to m divided by z. So from this equation we can conclude here that the maximum bending stress is inversely proportional to the section modulus. Since we are interested that the value of the maximum bending stress should be as low as possible, then the design is same. In that case the beam should be designed with a large value of z, because if the value of the z is large as possible, the value of the sigma b will be minimum. So you have to select such a cross section for which the value of the moment of inertia should be very large. For example, consider here we have a two rectangular beam, and in both cases the depth is higher value as compared to the width. In the first case we have depth is equal to 60 and the width is equal to 40. So in the first case we have area, that is a cross section area, will be h1 multiplied by b1 is same as equal to 40 multiplied by 60, that equal to 2400, let's say mm square. In the second case what we done is that we have reduced the width to 30 and height we make equal to 80. In this case also you will get the area equal to h2 multiplied by b2, that is we have 30 multiplied by 80, that equal to 2400 mm square. Means the cross section area in both the cases are same. But if you check the value of the section modulus for the beam 1, section modulus for beam 1 is z1 is same as equal to I1 divided by the value of c. In this case the top fiber and bottom fiber is equidistance, is same as equal to h1 divided by 2. So we have z1 is equal to I1 is same as equal to b1 into h1 cube, and these two will shift in numerator, and 12 of moment of inertia will write in denominator. In addition to that we have h1, so 2 and 12 become 6. So we have z1 will be equal to b1 into h1 square of it divided by 6. So we get the value of z1 here will be b1, that equal to 40, h1 equal to 60, we have square of it divided by 6. So we have a value of z1 here equal to is 24,000. Unit is mm cube. Same value we can calculate for the second beam, which has a higher value of depth as compared to the first one. We'll use this formula here, that is b2 multiplied by h2, we have square of it divided by 6. In this case the width is smaller as compared to the first one, that equal to 30. We have depth is equal to 80, which is higher as compared to the first case, and divided by 6. So we'll check here, the value of z2 will be higher as compared to z1, will come out to be 96,000, that will be mm cube. So we conclude here the value of z2 is greater than z1, and if the value of z2 is greater than z1, then the maximum value of a bending stress produced in the second case will be lower as compared to the bending stress in the first case. So if you want to use a rectangular section, then you should select the highest value of the depth as possible as compared to the width. So it is important what is the value of section modulus for us. Beam should always design with a larger value of Z as applicable, because the bending stress in the second case will be smaller as compared to the first case. Thus we conclude here is that the beam with a larger depth H will have a larger section modulus and thus will be more effective in resisting the bending. So we'll discuss here different sections and which section is best, that we want to find out here. So consider here a rectangular section of width equal to B and the height equal to H. This time we have maximum value of a bending stress at the top fiber and the bottom fiber. Now this section is not a very efficient section because firstly the large area is close to the neutral axis. So as far as the neutral axis is considered, we have a very large area. That is, we have a same area that equal to the rectangular area. And at this point here, we'll find here that the bending stress is very low value. So near this area, neutral axis here, we have very small distribution of bending stress. Bending stress is small, even the cross section is also very large. And where we have a maximum value of the bending stress, that time also we have same area. So this is not a good distribution of area over the stress. What we want is that if we have a smaller stress, then we should have a smaller area. And if we have a larger stress, then we should have a larger area. In the case of rectangular section, here the area is remains same here. So therefore the rectangular section is not a very efficient section as far as the bending stress is considered. So exactly what we want here, that this area should be smaller area. So in fact here what we desired here is that where we have a larger stress, it should have a larger value of the area. Like this one, it should have a larger area. Here also we have a larger stress, so this should have a larger area. And where we have a lower value of the stress, the area should go on decreasing. So ideally speaking, we have the I section is supposed to be the best section, because you find here for I section, where we have a stress is low, area is also low, and where we have a stress is maximum, the area is also maximum. So therefore the rectangular section is not a very efficient section as compared to the I section. Now let's consider here a circular section. Distribution of a circular section again is same as the rectangular section, because the top fiber and the bottom fiber is equidistant from the neutral axis. The distance of the top fiber and bottom fiber is same from the neutral axis, that equal to d by 2. And the second observation is that where we have a stress is very small, that time we have a very large area. So this is not desired. In fact, if we have a less stress, then we should have a less area, and therefore the circular section is not a efficient section. So near the diameter here, our distribution of a stress shows here that we have a smaller value of a bending stress, but the area is larger. So we have a less stress and we have more area. And in fact here what we want is that where we have a larger value of the bending stress, there we should have actually a larger value of the area, but this time we are having a very small area near the top fiber and bottom fiber. So where we have a more stress, then at that time we have in a circular section we have a less area. So this section is almost similar to the rectangular section, and we have added disadvantage is that as the bending stress increases towards the top and bottom, the area, that is a width, is decreasing. This is not a very efficient section, so this section you have to avoid while designing the beam. Now let's consider here the third area is a square area. In the case of the square area, we have a neutral axis here, and at neutral axis we have stress equal to 0. This time we have a same width equal to B, and we have same height, that is B. Width and height, they are same in the case of square cross section. So where we have a stress is less, we have a same width. So width is not changing. In fact here we required here is a smaller width, and if you have a smaller width, then we have the smaller area, but that is not so in the case of square section, and therefore the square section is also not a efficient section as far as the beam design is considered. So near the neutral axis here we have a less stress, but we have a same width, and we have a same width even we have a larger value of a stress, that is near the top fiber and near the bottom fiber. So here the width is remain uniform. So where the stress is actually more, at that section we want here the more area, that is a more width. That is only possible in the case of I section on the top and bottom fiber both, and therefore a square section is less efficient than the rectangular section for the same area, because for square section the moment of inertia divided by c, that is a section modulus, is a smaller value that already we have proved, and therefore the rectangular section is always a better section as compared to the square section, and the symmetrical I section is the best section as compared to the rectangular section also. Now let's consider here the I-beam section. So this section shown here for the structure work is normally used as a I-beam section. There are two types of I-beam section, one having a short flange and one having the wide flange. Wide flange is normally called as W beam. W stands for wide flange and S stands for here short flange. And the distribution of a bending stress again from the top fiber and bottom fiber here is shown here, and we have maximum value of a bending stress is either on the top fiber or bottom fiber, and at the neutral axis here where we have almost a zero stress. So contribution of a smaller stress, then we have a smaller area in both the case, that is a S beam as well as the W beam. So near the neutral axis here we have a less stress and we have a less area, and the maximum stress here is on the top fiber where we have either a short flange or we have a wide flange. But wide flange is a better idea because we have a more area as compared to the short flange. But you can prefer the short flange as well as the wide flange, both depend upon what is the value of the bending stress. So you will get an advantage of more stress when we have more area. So that is desired actually. If you have a more stress, then we must have more area. So our discussion is only applied to the beams which are subjected to pure bending. Our discussion is not included here the shear stress due to bending. So up till now the most efficient section is the I section, and even in the I section the wide flange beam, that is W beam, is more commonly used in the case of the structural work, because as compared to the other shapes here the large portion of their cross section is located far from the neutral axis. Thus for a given cross section area and a given depth, their design provides a larger value of moment of inertia I and correspondingly the higher value of section modulus. Now the same distribution we can also discuss for the T section, but the T section again we have the less area at the bottom. Distribution will not be symmetrical in the case of T section. We have a smaller area and we have a larger stress, and therefore the T section is also not a good efficient section. The best section is I section, and that too the wide flange W beam instead of the short flange S beam. Standard dimensions of W flange are available in the appendix. You can check the design data book and you can record the value of what is the size of wave and what is the size of flange and what is the total distance of the wave plus flange. One more section we'll discuss here, that is a hollow circular section, and in the case of hollow circular section, which is normally used in carrying the water, so the pipes are normally the hollow section and they are strong because the bending stress is a larger value at the top here and we have a larger area. So this is the almost a bending stress distribution here. On the bottom we have bending stress distribution will be something like this. So where we have a larger value, we have a larger value of the area also. So the hollow circular section is more efficient as compared to the solid circular section. So pipes carrying the water has to be supported at some distance is an example of a hollow circular sections. So this one is the effect of the beam section, which is entirely depend upon the section modulus. Higher the value of section modulus, lower will the bending stress. Lower will the value of bending stress, more safe is the design. And in the case of particularly wide flange W beam, we have highest value of the section modulus and therefore the less chance of the stress produced. Which of the following statement is correct? A square section is more economical in bending than a circular section of the same cross section area. Already we have shown this because the section modulus in the case of square section will be higher as compared to the circular section. The modulus of a square section is less than that of circular section of the same cross section. So we have given here one square section and one circular section, and it is given here the condition that the circular section and the square section have the same area. So to define here both 1 and 2, we'll find out here the section modulus for square section and the circular section. So let here we have one square section of side equal to A. So both the sides are equal, and let's say we have diameter equal to D. First you are given here that the cross section area is same. So let's equate them, the area of both square section and the cross section. So in this case the area of the square is same as the product of A into A, and the circular cross section is pi by 4 multiplied by D square. Solve this, you will get the value of D. So 4 is multiplied here, so we'll get here 4 times of A square divided by pi, that will be equal to D square. Or we have diameter D is equal to 1.128 times of A. So first we locate here the centroid of a square section. This one is representing the centroid of square section, and the value of C here in the case of square section is same either for the top fiber or bottom fiber. So this value indicates C here, and the value of C is same as A by 2. Similarly, we can look at the centroid of a circular cross section, and top fiber and bottom fiber again is at the same distance. So value of C is same as equal to D by 2. The section modulus Z is given as I divided by C, where C is the distance of the top or bottom fiber, which one is maximum. So in this case both values are identical value. So section modulus in case of square section is I divided by C. For square section we have the moment of inertia about the Z axis is A to the power 4 by 12, and value of C is same as A by 2. So we have A and 2 will shift in numerator. So this value will be same as equal to, one of the A will get cancelled, this 2 and 12, so 6 is we have A cube divided by 6. Similarly for circular section, the section modulus is given as I. We have I is equal to pi divided by 64 into D to the power 4, and the value of C here is D by 2. So we have multiplied by D, and 2 will shift in numerator. So this value is approximately equal to 2 and 64 32. So we have pi by 32 and D cube. So the Z for circular section is 0.098 into D cube. Here we can replace the value of D is equal to 1.128. So we'll get this answer equal to 0.098 multiplied by 1.128 times A, and we have to make a cube of it, is approximately equal to 0.161 times of A cube, and we have A by 6. A by 6 is same as 0.1666 times A cube. So clearly we observed here that the section modulus in the case of square section is 0.166 A cube, and the section modulus in the case of circular section is lower. It means that we have Z for square section is greater than the Z for circular section. As for the second choice here, the modulus of a square section is less than that of a circular section. So this one is a wrong statement. Maximum value of a bending stress is given as M into C divided by I, which is same as equal to M divided by Z. Means the bending moment is inversely proportional to Z. So in this case we can calculate the bending stress for square section and divided by the bending stress for circular section. So we have Z for circular section divided by Z for square section. So A cube and A cube will cancel out. Z for circular section is 0.161 and the Z for square section is 0.166. So this ratio here is less than 1. Less than 1, it means that we have bending stress in the square section is less than the bending stress in circular section. So this section is more economical as compared to the circular cross section. So square section is more economical. So choice 1 is correct. So in this case the statement 1 is only correct. Choice B is correct choice. The ratio of the moment of resistance of a square section beam Z When a square section is placed one with the two sides horizontal, so this is a square whose sides are horizontal, and the second one with a diagonal horizontal Z2, and this one is second figure in which we have diagonals are horizontal. So this one is the diagonal is horizontal. We want to find out here what is the value of Z1 and Z2. Z1 and Z2 is here same as equal to the section modulus. As far as the square section is considered, the centroid will lie at this point, and in the case of rhombus, it will lie at the intersection of two symmetry lines. The C value here is a maximum value of a top and bottom fiber in this. So this value is C or bottom value is C. So here the square section has a side equal to B. So value of C will be same as equal to B by 2. Here you have to do the little bit of calculation to find out this value of a top fiber or bottom fiber. Both are same value. So this angle is same as 45 as well as this angle is 45. So this vertical distance is hypotenuse is B and is 45 opposite side. It means that this distance is same as B times sine of 45, and sine of 45 is 1 by root 2. So this distance is same as B by root 2. This one is the value of C. Now as far as the moment of inertia is considered for figure 1, moment of inertia for square is B to the power 4 divided by 12. And as far as the rhombus is considered, the moment of inertia only depends on the side. So value of I2 is also equal to B to the power 4 by 12. Section modulus Z here is given as the ratio of moment of inertia I divided by C. Since here we have I1 is same as equal to I2, we can claim here we have Z1 C1 is same as equal to Z2 C2. And we have to find out the ratio of Z1 by Z2. So we have Z1 divided by Z2 is same as equal to C2 divided by C1. C2 here is B by root 2 and C1 is B by 2. So B and B will get cancelled, and here we will get C2 is 1 by root 2. So we have 1 by root 2. C1 is by 2. So we have 1 by 2. So in this case, we will get this ratio equal to root 2. Our choice C is correct. The video you are watching is from the app, which is the Mohod class app available on Google Store. And in this app, we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.